This is Professor Thompson again, and this is exercise 35 in 1.3. And so they want to know the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. And then we need to prove with the epsilon delta definition that it's 5. And so this is kind of an interesting one because this is the first limit proof we've done where you can't just plug the number in and check. Because you see, if I plug in 2, I get 0 in the denominator, and so this function is not defined there, but I can still show the limit exists. So we're going to just do this like we did all the other ones. So we're going to note the fact that because a is 2 here, and here's f of x and L, because a is 2, we're trying to get information about x minus 2. We want that to be less than delta. But we start by looking at f of x minus L, and we look at the inequality we get there when we say that's less than epsilon. So, if I take f of x minus L to be less than epsilon, f of x here was x squared plus x minus 6 over x minus 2, and L was 5. So with this inequality, we don't have much we can do yet because we're kind of stuck in the absolute value and we don't really have a way to work on both sides, so you have to think about this left side kind of like an expression. And so that means that one thing that we could do would be to do common denominator here. So the common denominator would just be x minus 2. And we've got x squared plus x minus 6 minus 5 times x minus 2. And it's all over x minus 2. And this whole expression is still less than epsilon. So now that we've got this expression, we need to simplify it, and hopefully things will pan out. And so I'm a bit out of space, so I'm going to create a new slide so you can just pause the recording while you copy that down. So I've got x squared plus x minus 6 minus 5x, but now the negative distributes, and I've got plus 10 all over x minus 2. So notice there is an x minus 2 in the denominator, but we need x minus 2 in the numerator, so I don't use that. I don't worry about that x minus 2 in the denominator yet. So now when I simplify the numerator, this is x squared minus 4x plus 4. And really, I kind of need to get rid of that denominator because I want the expression to look like just x minus 2 without a denominator. And fortunately, now I can see that the numerator here will factor. So that numerator factors as x minus 2 squared, and then I've got x minus 2 in the denominator, and that's all less than epsilon. Now, one thing to note here is that I'm about to cancel a factor of x minus 2, and I know I made a big stinking class about not canceling variables. The point that I wanted to make is that when you cancel variables, you change the domain, you change the definition of the function, because you're eliminating holes in the domain. However, what you should notice so far with limits is that holes don't affect the limit. If you create a hole or you fill a hole, the limit usually stays the same. So basically, the function was not defined at 2, or at least this difference, f of x minus L, was not defined at 2. But when I delete this hole, I kind of fill in the hole, and so I do change the function, but I don't change the limit. So it's okay. The point being is that it's okay to cancel here. So I end up with just x minus 2 in absolute value is less than epsilon. So after all that, we see actually our choice of delta should just be epsilon, because I've created the expression I wanted, x minus 2 less than epsilon. So now we go through our proof, and our proof we need to end up at the point where we have f of x minus L. So this will take a bit of work to go backwards. So our proof here is that I begin with epsilon being given, and then I choose delta equal to epsilon so that I can start by saying that x minus 2 is less than delta, or excuse me, is less than epsilon. So it's less than delta, but delta and epsilon are the same. So I can start here, and now I need to change this expression to f of x minus L. And so the first thing I'm going to do is to kind of undo what I just did. And so this is not something you would know unless you just did all that background work. So I kind of create a hole, but that's okay. That's not going to change the inequality. And now I'm going to expand that numerator. And so, thinking backwards again, I'm going to introduce in the numerator the 5x minus 10 that I had by separating the 4x and the 4. So what I'm going to do is I'm going to take minus 4x, I'm going to write that as plus x minus 5x. And so I didn't change anything, I just rewrote minus 4x as two different pieces because I need those pieces back. And then plus 4 I'm going to change to minus 6 plus 10. So the goal of this is that I can separate the denominator after I get the minus 5x plus 10 back. And another way you can see I'm creating the x squared plus x minus 6 that I originally had. So now I have x squared plus x minus 6, and then the other piece is really minus 5, and I can go ahead and factor in x minus 2. That's the minus 5x plus 10 that I just created. So remember, I'm using an expression, so all I did was, I didn't really do anything, I just changed the way I was writing things. I didn't multiply both sides or anything like that. I'm only working on the one side. But now I can separate the denominator. And now these x minus 2's will cancel. And after that, you see that the expression written is f of x minus L being 5, and it's less than epsilon. And that completes the proof.